Hi all, and welcome to this episode of Physical Attraction. A little bit of background here. I'm currently working on some scripts for an upcoming series, but it will take a little while for them to be ready. However, one of the topics that we were going to touch on has been in the news lately, and I got a listener request to discuss it in more detail. And I actually saw a very good talk, a lecture on this topic at Oxford a year or so ago, by Professor Elena April, who is actually in the news story that this is surrounding. So a lot of this discussion is going to be based on that talk. This is going to be a one-off episode in which we'll deal with this specific topic, slightly out of context, and when the series comes out we'll talk about it in a lot more detail later on. So what I want to talk about specifically is some of the experiments that are going on around the world right now to try and indirectly detect dark matter. But to do that, of course, we need to quickly explain what dark matter is. So what is dark matter? Well, dark matter is matter that you can't see because it doesn't interact with electromagnetic radiation. Consequently, it doesn't absorb, reflect, or emit electromagnetic radiation of any frequency, which is why we can't see it with our telescopes and can only infer that it's there based on how its gravitational pull affects normal matter. But of course, that barely answers the question of what dark matter actually is. Essentially, dark matter remains something of a mystery. Astrophysical explanations and observations suggest that perhaps 85% of the actual mass in the universe that gravitates, that is influenced by the force of gravity, is simply unaccounted for. We know that it has to exist because if it didn't, galaxies would fly apart, the cosmos would be expanding at a different rate, and we would be unable to explain lots of different observations, including, for example, observations of how galaxies rotate, within our currently accepted and very well verified theories of how gravity works. If you allow yourself to introduce a large amount of matter that can't be seen, though, the mathematical models of gravity then work with our observations and we can explain our observations more easily. I'm not going to go into too much detail here, but it does remain one of the rather crazy facts about astrophysics. We think that only around 1% of the matter in the universe consists of stars. Perhaps 7% is visible gas that forms in halos around galaxies. Another 7% is in the intergalactic medium, which is this vast, sparse plasma of atoms and electrons that fills the space between galaxies. But the overwhelming majority, 85% of the mass that is influenced by gravity in the universe, is dark matter. Now, lots of people have found this philosophically unsatisfying. It's almost as if we're just filling in all of the gaps in our existing theory with some convenient ingredient that we can't see. But the fact is that most alternative theories, such as modified theories of gravity, require things that are just as arbitrary and even more unverifiable to be true for everything to hold together, and the predictions that these theories have made in the past have not been borne out by the observations. Without going into too much detail though, we should say there's several different lines of evidence that we have that has basically led to this consensus that there must be some kind of dark matter. We have precision cosmology, so we have satellites like the COBE satellite, the WMAP satellite, the Planck satellite, and they all look in different ways at the cosmic microwave background radiation, which is this leftover radiation from early on about 300,000 years after the start of the universe. And this allows us to infer how much of the universe's energy must be gravitating matter, how much must be dark energy that's pushing the expansion of the universe, and so on. We also have work by Vera Rubin, who noticed a discrepancy in how galaxies were rotating. Typically, if you have a rotating galaxy, you can figure out how fast the rotation should be based on how much mass is towards the centre of the galaxy. This is, of course, because the gravitational pull of the matter further inside the galaxy acts as the centripetal force for the rotation. Typically, you would expect the rotational velocity to change as you go further out in the galaxy, due to the different amount of mass that's enclosed by the rotating stars towards the edge. Vera Rubin, she studied the rotational velocity of galaxies, and it turns out that you can't really understand the rotational velocity profile of galaxies, how they're spinning, from the visible disk. You would expect the rotational velocity to decrease as you get further out, but instead what it happened to do was get constant. It stayed constant, no matter how far out you went from the centre of the galaxy. And the only way of explaining this was that there was around 10 times more mass that's not visible than visible mass to explain the rotational profile of the galaxy. An even more obvious point of difference is the gravitational lensing. So, general relativity, due to the way that general relativity works, matter bends space-time and hence bends the paths that light rays can take, that photons can take. And we can see distortions in far-off galaxies, magnifications of things that are further away, that we know are due to this effect called gravitational lensing. And the strength of the lens, which is almost magnifying the light coming to us from certain directions, that depends on the amount of mass between us and the object we're looking at. So again, you can calculate this, and you can see that this gives us an independent way of determining how much mass is between the distant object and us. And since we can then do some actual observations and see how much visible mass there is, we again know that for a lot of these gravitational lenses, the only way that they can be as strong as they are is if there's more mass than we can see between us and these distant objects. And that means that there must be more mass in galaxies and in the universe than we can actually see. And all of this means that we're fairly confident that some kind of dark matter must exist. That it probably clumps together in halos, that it exerts gravitational influence on stars, galaxies, and the fabric of space-time in general. And this is the only way we can explain our astronomical and cosmological observations. But obviously it would be nice if we could actually detect this dark matter and learn a little bit more about what 85% of the actual matter in the universe is made up of. There are plenty of different theories as to what dark matter could be, but one theory that's been popularly explored amongst physicists are that dark matter is made up of particles called WIMPs, or weakly interacting massive particles. Now, why is this? Well, there are lots of supersymmetric and theoretical extensions to the standard model, which is that model that determines the particles that exist in the universe, which naturally predicts that WIMPs will exist as an extension to the standard model. For more, you can listen back to our series on particle physics, which was called Concealing a Hadron. But the thing is with particle physics and theoretical particle physics is there's actually lots of ways to get lots and lots of different particle predictions that fit into your theory. So I think the main reason that people have theorised about WIMPs and hoped about WIMPs is that it would be pretty helpful if dark matter was made of WIMPs, because then we would be able to detect it in some more direct ways than we would otherwise. So there are four fundamental forces: the strong nuclear interaction, which applies to baryons, electromagnetism, gravity, and the weak nuclear force. Now we know that whatever dark matter is, it can't interact electromagnetically, or we'd be able to see it, it would be visible matter. We are pretty sure that it can't be made of baryons, it can't be made of quarks, and it won't interact strongly because of what we know about baryons. So we don't think that it can be baryonic, purely because of observations of baryons in the universe. I won't go into that in too much detail, that's one for the cosmology episodes, but we essentially know that it's probably not going to interact via the strong force. We know that it interacts gravitationally, that's how we can detect it at all, but you have to hope that it might also interact via the weak force, and then we would have another way to study it and understand it and possibly detect it directly. If WIMPs are really the source of dark matter, then we might have some reasonable hopes for detecting them. Depending on the mass of the WIMP, we know that there would have to be a lot of them about. This is purely to account for the amount of dark matter that we know that there is. If you take some fairly reasonable estimates for what the WIMPs might be like, then you might expect that billions of them could be passing through your body every year. Of those, most will pass straight through, but perhaps 10 in a year could interact with an atomic nucleus somewhere in your body. You don't notice, of course, but if these figures were true, then we could perhaps put a detector in place that might possibly be able to detect some of these interactions directly, and determine if WIMPs truly are dark matter, or that if particles such as WIMPs actually exist in the numbers that they would need to do to constitute a large fraction of dark matter. One of the first papers that talked about this was a 1985 paper called Detectability of Certain Dark Matter Candidates by Widden and Gutman. The central idea here was pretty simple. Hope that WIMPs are relatively massive, and as the WIMP scatters off a nucleus, you might not be able to measure the WIMP itself, but you can measure the recoil in that nucleus, which is visible, and you'll be able to see how it's responding to the WIMP, and then you will have some signal that will tell you that a WIMP has been there. One issue here is really nailing down exactly how many of these particles you might be expecting to see, and how many of these interaction events you might be expecting to see. That way you know how sensitive you're going to need to build your detector, how big it will have to be, and what the signal is that you're really expecting to find with this direct detector. And that depends on all kinds of things. If the WIMP is heavier, you obviously need fewer of them to make up the dark matter that we know is in the universe. We also need to know how much of that dark matter is in the Milky Way. And finally, we need to know something called the interaction cross-section. In essence, this is really a probability. It has units of area, so sometimes people talk about it as the surface area that a particle would have to hit for a particular interaction to take place. So for example, you imagine that you have a nucleus. Let's say that the interaction cross-section was 10 to the minus 50 meters squared. Then, if a WIMP is going to interact with the nucleus, it would have to fly directly through this area. You imagine that it's point-like and it has no extent or size of itself. It would have to fly directly through this area that is 10 to the minus 50 meters squared in size. Those are obviously just example figures actually, but the point is you can see this as either a probability or you can imagine the particles flying through these cross-sectional areas. But basically the thing to know about the interaction cross-section is it simply measures how likely the particle is to interact with the nucleus target. So the expected number of WIMPs that you'll find depends on a number of particles in the Milky Way halo, how many there are, which we can tell from observations of the Milky Way, their velocity distribution, you can integrate over that, the number of nuclei that are in the target, the mass of the WIMP, which as we've said determines how many WIMPs there would have to be, and the theoretical interaction cross-section. Now, the issue we have here is that the interaction cross-section is not constrained all that much because we simply don't know all that much about what WIMPs are like and how their weak interactions with matter would work. We would only know these things if we've actually observed them. So if you're not detecting them, then it simply might just be the case that WIMPs interact less often than you hope they do. As dark matter detectors have got more and more sensitive, they have effectively ruled out types of WIMP that are happy to interact more and more regularly, and constrained both the interaction cross-section and the mass of the WIMP. You have to understand, of course, that if you have a less massive WIMP, then there are more WIMPs about, which means that you might get the same number of observations with particles that are less likely to interact because there's more of them. So it's a sort of multi-dimensional constraint that you're bringing in here, where as you observe fewer and fewer events, or as your detector gets more and more sensitive, you're ruling out some of the more common WIMPs, which would be the lighter WIMPs, and you're also ruling out some of the more likely interaction cross-sections, because you get to a point where you think, okay, we would have seen something by now if WIMPs had this sort of mass, or WIMPs were this likely to react with the target. And we now know that if WIMPs do exist at all, they have to be pretty unlikely to interact with ordinary matter. If you make a few assumptions, you can try and work out how many of these events you're likely to see. So one assumption that people like is that the mass of the WIMP is around 50 giga-electron-volts. Now, just in brief, for those who didn't listen to the particle physics episodes or don't know what I'm talking about, giga-electron-volts are units of energy. It's the same energy that an electron would have if you passed it through 1 billion volts as a voltage potential difference. But since E equals mc squared for particle physics, we can use energy and mass interchangeably. So giga-electron volts are used as a measurement of the mass of subatomic particles. And a proton is around 1 giga-electron volts in mass, so this WIMP would be about 50 times heavier than a proton. So you can see that actually the WIMP is about as heavy as your average nucleus in this sort of thing, as heavy as a nucleus with 50 protons and neutrons in. Given that the mass of an atom is only, mostly made up of nucleus and a very, very tiny contribution from the electrons, you can see that these WIMPs might be about as heavy as atoms. Now, if you assume a cross-section interaction of 1 times 10 to the minus 46 meters squared, which is the sort of range that we haven't necessarily probed yet and proved that these things don't exist, and this WIMP of 50 giga-electron volts in mass, you would expect that there would be 15 events per ton of detector per year that would transfer enough energy that we might be able to detect them. So let me say that again. 15 events per ton of detector material per year. And now you can really see why the search for WIMP dark matter has been so difficult. Not only do we really not know what we're expecting to find, and so there's not really a characteristic signal to look for that we can unambiguously say would be dark matter, but if we have a target made of xenon, we'll talk more about why later, even if you have 1,000 kilograms of xenon as your target, then these parameters for the WIMP, which are considered quite reasonable, you'd only see 15 events in a year. That's an extremely low rate. And of course, because this is physics and particle physics, observing just one event isn't going to be enough. You'd want to build up significance and assure yourself that you're really seeing something that genuinely could be a dark matter signal and isn't just a coincidence or some other kind of rare interaction. And as with many physics experiments these days, the real challenge of the experiment, and the real triumph if signals are detected, is correcting for the background noise. To say we're looking for a needle in a haystack is unfair. We're looking for an atom of the iron that would make up a needle in a haystack. There are huge amounts of background noise from all sorts of different sources that could potentially produce similar recoil signals in the atoms of our target. Consequently, the process of making these detectors is very difficult. They must be very massive and very able to distinguish the weak WIMP signal from a huge background noise. For example, every hour there are 30,000 radioactive decays in your lungs. There are 15 million potassium atoms inside you that decay every hour from bananas and food. Natural radioactivity in the earth and in the buildings that surround us and the material that they're made up of sends millions of gamma rays through us each hour. Intrinsically, this background of events can potentially interfere with your detector and mimic an unusual signal. So to reduce this noise as much as possible, every element that's in the detector is screened as much as possible to reduce its radioactivity. And it can take months to screen these things and make sure that there's nothing radioactive in them. This can make things extremely difficult to arrange things with manufacturers. Imagine you're making this kit and some wire or something breaks. Well, you can't just order one off the shelf. If you want a new metal case for the detector, again, you can't order one off the shelf. You have to have it made to these incredible standards of low radioactivity, and it can't be contaminated by radioactive things on the way in. And this is not something that is usually considered from your sort of standard wire that you might pick up the shelf of B&Q. Trying to identify the lowest activity material appropriate to build a detector is very difficult, which is why lots of different types of detector have been tried. Now, neutrinos and neutrons, but mostly neutrinos here, are both quite large problems because they can behave exactly like WIMPs in the detector. You'll remember from the episodes on particle physics, or from your own knowledge, that neutrinos are these ghostly neutral particles which, by and large, pass entirely through the Earth without interacting with ordinary matter. The process for detecting a neutrino is quite similar to the dark matter detection methods because they're another type of particle that just occasionally interact with ordinary visible matter. You generally, to do that, you have an extremely large detector weighing many tons, which aims to find and observe the rare interaction between the neutrino and the conventional matter. But filtering out a neutrino background is not particularly easy. 100 trillion neutrinos pass through your body every single second. Mostly these are produced in interactions that are occurring in the sun and streaming towards the Earth alongside photons of light. And almost all of them travel directly through the Earth and pass through the other side. There's not much you can do to shield against that when it's capable of going directly through the Earth. So, essentially, the race to detect WIMP dark matter directly with one of these machines has always had this innate limit. They call it the neutrino floor. So that's a certain limit beneath which you're looking at the neutrino flux background and not WIMPs, and you won't be able to distinguish any WIMP signal from the neutrino interactions in your detector. You can sort of imagine this as if you're listening to some music with an awful lot of static in it, and you're trying to listen for a particular tone. And that particular tone is going to be buried underneath this white noise if the white noise is loud and the tone is quiet enough, so that you won't be able to detect it at all. That's really what's happening here with this neutrino floor. Now, for quite a while, this was a theoretical limit because our detectors weren't that good. But as the direct dark matter detectors have grown more and more sensitive, there's been a deep concern that they may well reach the neutrino floor without finding anything. And in fact, you'll remember we talked about how there are two parameters here. There's the cross-section and the mass that you need to worry about. And for some masses of WIMPs, we've sort of ruled them out in the sense that if the WIMP did have that mass, then its interaction must be rare enough to be below the neutrino floor, and we're not actually seeing it at all. So as the detectors grow more and more complicated, there's been a real concern that we'll reach this neutrino floor and all we'll be able to pick up on is background noise. Will be sensitive enough that we can hear this static and we can't hear any tones, and so we'll never know whether the WIMPs are actually there or not. New generations of detector are being constructed all the time, and they're gradually ruling out lots and lots of these different potential properties for dark matter. And we now know that if it exists at all in the form of WIMPs, it's going to have to be a kind of WIMP that interacts with ordinary matter very rarely indeed. Now you might be asking yourself, how do we know that the dark matter signal is above the neutrino floor? And the answer is that we simply don't. And in fact there's no real reason to expect that it might be. We build our detectors in hope rather than expectation. It's perfectly possible that dark matter does exist as WIMPs, but that these WIMPs interact so rarely that we'll never be able to distinguish it from this noise background of neutrinos. At least not with the kind of experiments we can conceive of today. And of course it's equally likely that, and of course it's also possible that dark matter doesn't exist as WIMPs at all, and that whatever dark matter is made up of just doesn't interact weakly at all. We don't really know. But this is the thing that we can do, is to build these detectors and hope that, frustratingly, these millions of dark matter particles that may exist stream through and give us these interactions. This is what struck me when I watched this talk, realising how close the experiments have come to the neutrino flaw in recent years. It's an incredible achievement on behalf of the experimenters, but it seemed a couple of years ago that it might be that they had all spent decades producing brilliant experiments that merely conclusively ruled out finding detectable dark matter in this form. And of course that's important work, but you have to wonder whether the people who are engaged in these experiments would really find that as satisfying as the discovery of dark matter, which would probably win them all Nobel Prizes. So it's worth saying in this that a vast array of different types of detector have been tried. So back in the day, people used to use bubble chambers. These are charged particles. When charged particles move through this supersaturated liquid, they leave these trails of bubbles, and you can see these sort of things being used to observe the tracks of particles from CERN. A lot of old particle physics was done in this way. It's a little bit passé now because you can't detect quite as many things with a bubble chamber, but if you ever get a chance, look up some footage, or indeed in CERN itself there is one which they have a little radioactive source feeding into, and you can sort of see the different patterns that are produced by different particles of different charges. So bubble chambers have been used, noble liquids have been used. There's not much radiation in these, and you're looking for these nuclear recoil that we talked about. One thing that people have used is cryogenic bolometers. So these are really, really cold detectors, and they will be at a very, very low temperature. And therefore, if energy is transferred into them, that will be a considerable temperature change that you're going to be able to detect. So they're looking for the small temperature changes that are going to occur due to these collisions. Another thing that people have tried is scintillating crystals. So this is an idea of a crystal where you have a big lattice, and if something bashes into one of the nuclei of the crystal, it sets it off vibrating altogether. And if any interaction sets off these big oscillations in the crystal, you might be able to detect those big oscillations more easily than you will be able to detect a single nucleus recoiling. So that's the idea behind them. Some of the detectors that people have used are directional. So this does make quite a lot of sense, really, is to see if there's any difference in the directionality of the detection. So, for example, you might want to point the detector in the direction where the solar neutrino flux is the weakest, so that your background noise effect is as weak as possible. Because we know that all of these neutrinos are coming from the sun and nuclear interactions in the sun, and that's where most of them will come from. But we don't actually have any expectation of dark matter coming from the same direction. So you would expect the peak dark matter signal to be in a different direction. So if you can work on these directional detectors, then you might be able to see if there's any difference in these backgrounds, which you would then notice as a significant result that comes from WIMPs. So some of these detectors have names like Simple, Picasso, Q, Pico, Super CDMS, Edelweiss, Crest, Cosinus. There have been many, many different types of detector built over the years. So when you imagine these detectors, you have to essentially imagine this sort of unusual setup. It might be that you have something in an underground laboratory, a long distance away from anything else to cut down on the radioactive background signal. You might have a detector that consists of many tons of cryogenically cooled material, or a carefully arranged crystal lattice, or a huge liquid xenon chamber somewhere. Deep underground, the detector waits silently, passively for years, hoping that rare fleeting blips will emerge that could be the signals of a ghostly dark matter particle, alerting us to its presence by a very uncommon interaction with visible matter. So for many years, the field has been extremely competitive between some of these different types of detector, but over the last 10 years or so, liquid xenon detectors are getting better and better. To illustrate what this means, we think of this interaction cross-section for a 50 gigaelectron-volt WIMP. Over recent years, since 2000, these have probed from 10 to the minus 40 centimeters squared to 10 to the minus 47 centimeters squared. So in other words, they've got around 10 million times more sensitive over the last 20 years, and they're approaching the neutrino flaw at 10 to the minus 49 centimeters squared. So you can see that actually if things go on, the next generation of detectors that will be built will take us right the way down to the neutrino flaw, and then we either find something or we don't. It's game over for dark matter one way or another. detectable in this way, I suppose you should say. The detectors are now so sensitive that they can detect one event per ton of detector material per year, which is a crazy statistic. A whole year you have this ton of detector material sitting around, and it can actually be sensitive enough to pick up on just one event in that whole year. What happens if we hit this neutrino floor? Well, technically we still can't rule out the idea that WIMPs are the solution to the dark matter conundrum. All we know for sure is that we can't detect them directly in this way, because this coherent neutrino scattering will get in the way, and then this direct hunt will basically be over. So when I saw Professor April a couple of years ago, she described her work on the Darwin, which was the dark matter WIMP search with liquid xenon, which is looking for this whole region, looking through this whole region for heavy WIMPs right the way down to the neutrino floor. And in the next decade or so, she said they'd either find detectable WIMPs or rule them out altogether. So what are the advantages of these xenon detectors then? Why are they leading the way? Obviously, Professor April was a little bit biased because this is the thing that she invented. She invented the xenon detector for detecting dark matter, but she did illustrate that it has a lot of different advantages. So, as a reminder, xenon is a noble gas. It's the heaviest if you exclude radon. You can't use radon in this because it's radioactive, so obviously it's a terrible material for this kind of detector. Xenon has a large nucleus, which is good for heavy WIMPs, as your scattering will be detected more easily. When liquefied, it's a dense liquid, which is good because what you want is a really heavy target, but you want it to be quite compact and you want it to be homogeneous. That is to say, you don't want there to be differences in density there. You want a sort of nice, dense liquid that you can fit in many tons of detector material, lots of nuclei close together in a small detector. And that's going to maximise your chances of observing the scattering event, and it will help you to reduce background. The cryogenics are easy for xenon. There are these mature technologies that can liquefy it and keep it very cold for a long time, so you don't need to worry about those sort of things. And finally, if you did have a WIMP interaction, there are two different kinds of signal that you can get. The xenon might be ionized by the interaction, so an electron might be knocked off the xenon atom altogether. That would produce a light signal, because another electron is going to come in and recombine with the xenon, and that's going to release a photon which you can then detect. And there's also scintillation, so in simple terms, you can imagine the WIMP hits this in this interaction, the nucleus recoils, this can ionize the nucleus, or it can send the atom into an excited state and cause photons to be emitted as the electron de-excites in the xenon atom. And there would also be a signal of heat from the elastic scattering of the nucleus. Now, the type of detector they're using at the moment can't actually detect this heat, but it's the sort of thing that some of the crystalline detectors are looking for. It just so happens that xenon as a target produces quite a large number of photons per interaction, so that you get a particularly noticeable light signal when you use xenon if one of these interactions does take place. The type of photon you might get if xenon was excited and then de-excited in such an interaction is this particular line at 178 nanometers. That's in the high UV spectrum, and we know how to detect this sort of radiation pretty well. But of course, manufacturing the phototube, which is going to try and detect it, is again a challenge because it can't be a radioactive material at all. There are some other advantages that she mentioned too to using xenon. It doesn't have much background radioactivity as a material. There will be trace amounts of krypton in it, but once you do that, it's not radioactive at all. It only costs around $2,000 per kilogram to produce, which is substantially cheaper than gold, though you can see that it does mean that the xenon is going to cost around $2 million, so this isn't the sort of detector that you could easily build yourself in your garage. And that means that if you have a budget for xenon, then you're going to be able to make a slightly bigger detector than you might otherwise if you were using other more expensive materials. And finally, in xenon, because of how dense this liquid is, and because of how heavy the nuclei are, the mean free path of gamma rays is only a few centimetres, so gamma rays don't make it very far into the material without being absorbed. So if you consider the evolution of the particular set of detectors that she's worked on since she first invented the xenon detector, the first was the Xenon 10, that had 5 kilograms of xenon, then the Xenon 100, which was 34 kilograms of xenon, and the newest one is 1 ton. And the advantage that these things have had is they've reduced the background quite immensely. So essentially, back in the day with the Xenon 10, you would get a 1,000 background events per ton per kilo electron volt per day. So that's the number to think of, is 1,000 background events per day, more or less, per ton of material detection. Then the Xenon 100, that was only 5.3 events per ton per kilo electron volt day. And the newest detector is actually just 0.2 events. So if all the detectors had been the same size, you've gone from 1,000 events a day to 5.3 events a day to 0.2 events per day in the background. So it's not just about building bigger and bigger and bigger detectors, but instead reducing the background that arises from materials and other procedures as much as you possibly can. And over the years, with successive improvements to these devices, they've reduced this background to an amazingly small rate, which is what's allowing them now to detect very rare events that are happening. And there's now some work going on building the Xenon N-ton detector, which would take us right the way down to the neutrino floor if it works as intended. That's being built in the Gran Sasso lab. You might remember that this Gran Sasso lab was the one that gave us that faster-than-light neutrino signal some years ago that turned out not to be true. There are some other labs like Snow Lab and the Jinping lab in China. The Gran Sasso lab isn't as deep as those labs, but it is deep under the mountains, which makes it a good place to look for these things because your background is naturally going to be quite low. Describing collaboration a little bit, there are 170 scientists in the Xenon collaboration across various different universities. There are postdocs and grad students from all over the world. One advantage that the professor pointed out is that the size of the detector is relatively physically small compared to something like the LHC. It would fit on the top of a table, this detector. And that means that if you're working on it, you can contribute to every aspect of it. Something like CERN is a much bigger collaboration. There's tens and tens of thousands of scientists there. You'll never know them all, whereas if there's 170 scientists in the Xenon collaboration, you might get to work with most of them. And the thing with CERN and Atlas detector in the LHC is that you'll only ever work on your little bit, and you might never know all of the other people working on the same project. So in some ways, the Xenon thing might be more satisfying to work on if you like being part of a team that size. Now, back in 2018, when Professor April gave this talk, they didn't have an awful lot of exciting results to show from the 1-ton detector. None of the events they detected could have been a WIMP. What they were looking for was a 3 sigma excess, in other words, something that's very unlikely to have occurred simply by chance. But at the time, the results that they had were consistent with the hypothesis that WIMPs don't exist, so all they'd done is rule out a bunch of different possible WIMPs in terms of their potential mass and cross-section to interact. But there were some cheering results. They had found that their device was better than competing devices, meaning that it remains a state-of-the-art dark matter detection unit. And they also did observe the rarest decay on Earth that's ever been seen in a detector. So the radioactive decay that they observed was called the 2-neutrino double electron capture in 124 xenon. So what happens here in this incredibly rare interaction is that 2 protons in the xenon atom spontaneously and simultaneously absorb electrons in electron capture. Those protons become neutrons, and so you have a new element formed, tellurium. And this is pretty amazing here. The half-life for this interaction is 10 to the 22 years. In other words, 1 trillion times the age of the universe. If you had an atom of xenon just sitting around, you'd have to wait 1 trillion times the age of the universe just for it to have a 50-50 chance of this interaction happening. Obviously, because they have more than 1 trillion atoms in place, you're able to observe this every few years with their device. So what this has showed at the time is that the detector is capable of seeing very, very rare events, even though it wasn't necessarily designed to observe them. Unfortunately, though, they had actually seen too many of these events to be convinced that they were WIMPs. The signal that they're looking for is much smaller than that. So it's just another source of background that they have to kind of eliminate from this detector and take into account when they're looking for WIMP-like signals. So that was the story when I saw this talk a couple of years back. The collaboration had built this incredibly impressive detector, capable of detecting these incredibly rare events, but they hadn't found what they were looking for, which was evidence of dark matter. Now, though, this may have changed, although not in the way you might expect. And this is the story that caused me to dig out my notes from the talk and write this episode. Because Xenon 1T has found something that looks like a signal. But if it is a signal, it's not from WIMPs, but instead possibly from axions, a competing dark matter candidate particle. Quoting from the brilliant Natalie Walchover at Quantum Magazine, who wrote up this story, she wrote, quote, "The physicists who run the world's most sensitive experimental search for dark matter have seen something strange. They've uncovered an unexpected excess of events inside their detector that could fit the profile of a hypothetical dark matter particle called an axion. Alternatively, the data could be explained by novel properties of neutrinos. More mundanely, the signal could come from contamination inside the experiment. That would be due to tritium atoms that have not been discovered yet." The collaboration wants to finish work on the xenon N-tons experiment, which should start operating later this year, to be sure that the signal is not from this contamination. Quote, "If this turns out to be a new particle, then it's a breakthrough we've been waiting for the last 40 years, said Adam Falkowski, a particle physicist at the Paris-Saclay University in France who was not involved in the experiment. You cannot overstate the importance of the discovery, he said, if this is real." So, we've been discussing on this show how Xenon 1T was hoping to find WIMPs using these nuclear recoils, but as they built successively more sensitive detectors, they weren't seeing any excess of these events. Professor April is actually quoted in this Quanta article describing the whole process as a desperate saga. But instead, what they've actually detected is an excess of electron recoils. From Quanta again, quote, "As the WIMP search kept coming up empty, xenon scientists realised several years ago that they could use their experiment to search for other kinds of unknown particles that might pass through the detector, particles that bang into an electron rather than a xenon nucleus. They used to treat these electronic recoils as background noise, and indeed many of these events are caused by mundane sources such as radioactive lead and krypton isotopes. But after making improvements to drastically remove the background contaminations over the years, the researchers found that they could look for signals in the low-level noise. In their new analysis, the physicists expected to see electronic recoils in the first year's worth of Xenon 1T data. They thought they'd see around 232 of these recoils, caused by known sources of background contamination. The experiment saw 285, a surplus of 53 that signifies an unaccounted for source. After rejecting all possible sources of error they could think of, the researchers came up with 3 explanations that would fit the size and shape of the bump in their data plots. First and perhaps most exciting is the solar axion, a hypothetical particle produced inside the Sun that would be similar to a photon but with a tiny amount of mass. Any axions produced recently in the Sun couldn't be the dark matter that had shaped the cosmos since primordial times. But if the experiment had detected solar axions, it means that axions do in fact exist, which is not something that we know for sure right now. Such an axion could also be produced in the early universe and then would make up some component of dark matter, said Peter Graham, a particle physicist at Stanford University who has theorised about axions and ways to detect them. Researchers said that the energy of solar axions inferred from Xenon 1T's bump doesn't fit with the simplest models of axion dark matter, but more complicated models can probably reconcile them. Another possibility is that neutrinos, the most mysterious of the known particles of nature, might have large magnetic moments, meaning they're like little bar magnets. Such a property would allow them to scatter with electrons at an enhanced rate, explaining the surplus of electronic recoils above what you would expect. Graham said that neutrinos possessing a magnetic moment would also be very exciting since it indicates new physics beyond the standard model. But it's also possible that trace amounts of tritium, a rare hydrogen isotope, are present in the xenon tank, and that their radioactive decays generate electronic recoils. This possibility, unfortunately, can neither be confirmed nor excluded, wrote the Xenon 1T team in their paper. So, unfortunately, I don't want to rain on anyone's parade when it comes to this story, but as we generally find with these experimental physics stories that are really pushing the boundaries of our ability to detect things, when you get an unusual or an unexplained signal, it's quite often down to some experimental error or background that you haven't accounted for, even when you think that you've accounted for everything. And that's what you should assume it is until you're very convinced otherwise. Quanta again points out that the axion theory and the neutrino theory both seem to be contradicted by measurements from astrophysics. They said, quote, "Outside researchers say there are not red but orange flags, as Falkowski put it, that point to a boring answer. Most importantly, if the Sun creates axions, then all stars do. These axions would be leaking a very small amount of energy away from the star, like steam carrying away the energy of a boiling kettle. In very hot stars, like red giants and white dwarfs, where axion production should be the greatest, this energy loss would be enough to cool the stars down. A white dwarf would produce so many axions that we wouldn't see hot white dwarfs around today like we do, because these white dwarfs would be cooling down due to these axions. Neutrinos with large magnetic moments have been similarly disfavoured. In comparison to standard neutrinos, more of them would be spontaneously produced inside stars, sapping away more of the star's energy and cooling down hot stars more than is observed." End quote. So both the axion and the magnetic moment of the neutrino idea would create some contradictions between these particles existing and being produced in a way that could be seen in the detector, and some of the astrophysical observations that we have of stars that would have to be reconciled. Now, it's not impossible that these astrophysical observations are wrong, or that some other process is explaining how these things can happen at once, but it does make you think that these are slightly exotic and perhaps unlikely solutions to this problem. So I think most people would, if you ask them to bet, would suggest that this new result is most likely down to tritium contamination, and background radiation in the detector, which is not yet accounted for, even though I'm sure the team has been incredibly diligent at looking for this background radiation. There are lots and lots of ways that background radiation can get in there. And as we've talked about, these detectors are really operating at the very limits of what's possible. And of course, these detectors weren't originally built to look at these electronic recoils. They were built to look at these nuclear recoils. So there is a certain question as to whether there is still maybe some level of background that hasn't been eliminated from that type of detection. So these alternative theories, they seem unlikely, and you can't be sure that all these background events have been fully considered when what they're looking for is WIMPs, and now it's trying to be used to detect axions or neutrinos with magnetic moments. I didn't look into whether there are other experiments that are detecting neutrinos with magnetic moments or axions, but I would imagine that there would be somewhere, and if not, then they probably will find that maybe some people will start to, pivot from WIMPs to looking for these things instead, with slightly different types of detector, now that the WIMP hunt is looking increasingly unlikely. So the story of the xenon detectors in the last few decades is still really fascinating, and I think very much worth telling in my mind, though, because in the next few years we will know for sure whether our leading dark matter candidate in the WIMP is going to be possible to detect here on Earth or not. If it's undetectable, at least in this way, that's still a result, and will probably motivate a whole heap of alternative theories as to what dark matter might be made up of, and maybe even some different ways of trying to detect if it is made up of WIMPs in some other way, hopefully with some testable predictions that will allow the hunt for this mysterious 85% of the universe's matter to continue. Now, the mystery of dark matter in general might still be outstanding, but the mystery of this particular signal, luckily, is due to be solved pretty soon. When the xenon N-ton detector goes online later this year, the scientists involved in the collaboration suggest that they'll only need a few months of data and analysis to determine whether there's really something there for this unexplained signal. And at the same time, once this xenon N-ton detector has fully reported all of its results, we will basically, hopefully, have essentially found WIMPs or ruled out the idea of ever finding them on Earth in this method with a few years. So, in some ways, this is the last chance saloon for direct dark matter detection, at least in the way that we think of it now. And it's a reminder that, as much as we know about the universe, there's still so much we don't know, cannot say, and which could remain unexplained for many years to come. Thank you for listening to this episode of Physical Attraction. You can find us on the web at physicspodcast.com. There you'll find the contact form, comments, questions, concerns, topics you'd like us to cover, like this one, which was suggested to me by a listener, are all things that you can send us there, and we will respond to them as quickly as possible. I like to respond to people's emails, so in that case you might get a response, and who knows, you might get a whole episode out of it. We're on Twitter at PhysicsPod, on Facebook at Physical Attraction. You can support us by going onto the website where you'll find the PayPal link for one-off donations, the Patreon where you can subscribe and get all of the bonus episodes that we've produced so far. You can also support us by reviewing the show, iTunes, whatever your podcast platform is. Any sort of review you can put up there is always helpful for people when they discover the show. Let them know what you like about it. And let me know what you like about it, or what you don't like about it, via the comments form on the website. Of course, the best thing you can do to help us is always to tell other people who might be interested in the show to listen out for it, and catch us next time. Until then, take care.